Hello, game theorists. Today we're still looking at simultaneous move games. We used strict dominance to help us find a Nash equilibrium in the previous episode. However, it doesn't always get us all the way to the answer. It can cut down some of the possibilities and eliminate some options, but sometimes it doesn't lead us fully to the Nash equilibrium. So now we'll develop a second tool to find Nash equilibrium. This one is called best response analysis. This is the tool that I use most often, and most likely you'll be using it a lot as well. So what's so great about it is that it does find a Nash equilibrium quite reliably. We said earlier that dominance does not always get you there, but this one does. And it also applies to all kinds of simultaneous move games. Tool number 3, which we'll see later, only applies to zero-sum games, but this one works for zero-sum games and for non-zero-sum games. So we'll develop it with an example. This example is known as the chicken game. And we'll see this example actually reoccur several times in this course. So the way the chicken game is set up, it used to be played by teens in the mid-1900s or so. They would drive cars toward each other, and you have two options when you're driving towards your opponent. You can either keep going straight, or you can try to swerve to avoid them. So if you both go straight, you're going to collide, and that's obviously not going to be very good. So the way the game works is that the first person who swerves and another person who's going straight, the one who swerves is the chicken, the coward that is, and the one who goes straight is braver, and I guess they get all the glory from their courage. If they both swerve, though, they definitely avoid collision, but they both look like cowards. So there's you and there's the opponent. So if you both swerve, you're both cowards and you get payoffs of 0. If you both don't swerve, you collide, get into a big accident, that's minus 100 each. Now, if you swerve and your opponent doesn't, then you're the chicken, you're the coward, and you get minus 20 because your friends all make fun of you. Remember, role players' payoffs always come first. You're the role player, so your payoffs to minus 20. Your opponent gets all the glory from winning and being courageous, so they get a payoff of positive 20. And it's symmetric, so if you don't swerve and your opponent swerves, you're the brave one getting plus 20, and your opponent gets minus 20. Because they're the coward who swerved to avoid collision. So I realized a few months ago that with the pandemic, we routinely play a version of the chicken game. If you go for a walk and you're on the sidewalk going this way, and somebody else in the sidewalk going the other way, then you've got to try to avoid each other, because if you go within 6 feet, you could spread the coronavirus, or could get the coronavirus. So someone's got to go cross the street or go step off the sidewalk to give the 6 feet distance. And I guess the one who is doing that is the coward. The one who keeps going straight is the brave one. So I think of that when I take walks these days. So let's try to analyze this game. So one appeal to best response analysis is that it can succeed in places where strict dominance does not. we can verify quickly that there is no strictly dominant strategy. So if your opponent is playing swerve, then you're better off playing don't swerve. So you probably get 20, then get 0. However, if your opponent plays don't swerve, in that case you're better off playing swerve and getting negative 20. Negative 20 is better than getting minus 100. So sometimes you want to don't swerve, sometimes you do want to swerve. It's not like one strategy is always better. This game is symmetric, so the same is true for your opponent. There is no strictly dominant strategy. So tool number 1, which we had in the previous episode, just wouldn't apply here. There are no dominated strategies to rule out. So here's how best response analysis works. You look at each of your opponent's strategies. For each one, you figure out what would be my best response, hence the name best response analysis. So if your opponent plays swerve, what is your best response? If they're playing swerve and you also swerve, you get 0. Now, if they're playing swerve and you play don't swerve, you get 20. That sounds better than 0, so we'll play don't swerve in response to swerve. Now, I know it's a simultaneous move game. We move at the same time. We don't actually know in advance if they'll swerve or don't swerve. Rather, it's an exercise asking that if we knew what they would do, here's how we would reply. So I put an underline there to indicate this. So now we look at what if we knew in advance somehow that our opponent is playing don't swerve. If they're playing don't swerve, we're in this second column over here. We're the row player. We care about the first numbers, so the minus 20 and the minus 100. We're better off with minus 20, so we'd rather play swerve if we know in advance that they're not going to swerve. Now you got to do the same thing for the opponent. Suppose your opponent knows that you're playing swerve. That means they're going to be in this top row over here if you play swerve. Your opponent's the column player. Column players' payoffs always come second. That means they're considering this number and that number. Well, 20 is better than 0, so they'd rather get the 20. That means they're going to play don't swerve if you are playing swerve. Last part, if you play don't swerve, then we're in this bottom row. Column player, the opponent's payoffs come second, so they care about these numbers. They'd rather get the minus 20 instead of the minus 100, so we give that an underline for them. So the way best response analysis works is the payoffs that are underlined for all players in the same cell, those are Nash equilibria. So here we have 2 Nash equilibria. So there's one where you play don't swerve, and one where opponent plays swerve. Sorry. Let me restate that. There's one where you play don't swerve and your opponent swerves. There's another one where you play swerve. That's this one here. While your opponent is not swerving. So that's how you find the Nash equilibria. Now, again, Nash equilibria is the set of strategies, not the payoffs. So this is right if you're, say, something like Nash equilibrium is 20 minus 20, or minus 20 positive 20. That's not right because those are the payoffs, not strategies. So don't do that. Again, it's always the strategies, not the payoffs. So we can revisit one of our earlier games and use best response on that one. So earlier I talked about this game back here with Joanne and Jerry. We showed that Bx is a Nash equilibrium, but there's actually another one in there as well. So let's go through our best response analysis. Let's start by looking at things from Joanne's perspective. Suppose Jerry's playing X. Now, again, to be clear, I ask these questions as if we know in advance what the opponent's doing. However, even though we don't know what our opponent's going to do in advance, this approach is still valid for finding Nash equilibria. So let's say we know somehow that Jerry's going to play X. What should Joanne do? Joanne has two best responses to X. She could play A and get 0, so we'll underline that. Or she could play B and get 0. That also gets underlined. So you could have more than one best response. That's okay. Just underline both or all of them in that case. The one strategy that is not a best response in this case would be C, because C gives Joanne -1. As always, role players' payoffs come first. So that's what we'll do if Jerry is playing X. What if Jerry is going to play Y? So if Jerry plays Y, Joanne's best response is to play A. That's because A gives her 2, B gives her 1, which is worse, C gives her -1, which is even worse than that. So A is clearly best in response to Y. Now we look at things from Jerry's point of view. Suppose Jerry knows that Joanne is going to play A. Oh, sorry, I miswrote this. I meant to have this be a -1. So that will affect our results here. Okay, -1. So if Joanne is playing A, Jerry looks at the second numbers because he is the column player. Column players' payoffs always come second. Jerry would rather get 0 than get -1. If Joanne plays B, Jerry would like to play X and get 7 instead of getting just 1. If Joanne were to play C, then Jerry would like to get -2 from from plane y instead of getting minus 3 from plane x. So that does our best response analysis. We just got to look at where do we have all the payoffs being underlined. That happens in two places. So AX has 2 underlines and BX also has 2 underlines. So those are the Nash equilibria. Now this over here, AY is not a Nash equilibrium. That's because it only has 1 underline. Similarly, CY is also not a Nash equilibrium since it also has just 1 underline. So that wraps up that example and our section on best response analysis. In our next section, we'll learn about another tool which is called Minimax.